Hi, all. Today we are going to see about the GNN showdown. So before jumping into our series, I just want to explain how this series actually works. Because understanding the structure will make every episode land better. This series has 10 byte roadmap. It is a complete research-driven blueprint covering everything from raw structured claims data through classical ML baselines into graph neural networks and all the way to production deployment and real-time fraud pipelines. Every byte in that roadmap gets covered, nothing is dropped. But here's the thing, the roadmap is structured for coverage. The delivery is optimized for learning. That means the order you see in the roadmap is not always the order I explained. Some bytes get combined because certain topics are so deeply entangled that separating them creates a confusion. Graph construction and GNNs, for example. You can't fully understand one without the other in front of you. So I bring them together. Some topics get reordered because the intuition builds better a different way. What this means for you. If you are tracking the roadmap, don't worry if the given episode blends 2 bytes or touches a topic earlier than you expected. It's intentional. The content is all there, just sequenced for maximum clarity and real world intuition. Now we will jump into our episode. So today we answer the question that should be on every data scientist's mind the moment they decide to apply GNN to healthcare fraud. Which architecture actually works? Not in theory, not in a toy graph. On real Medicare claims data with class imbalance, heterogeneous edges, and the operational constraints of a production fraud system. GraphSAGE, GAT, and RGCN go head to head. These are some of the graph models. By the end of this episode, you will know exactly which one to reach for and more importantly, why. Now the hook here is $100 billion every year that the FBA estimate of what healthcare fraud cost the US system. Not a rounding error, a systematic coordinated theft that scales because it's designed to look ordinary. Here's what I want you to internalize before we go further. This is not a detection problem, but it's a network infiltration problem. Fraudsters don't operate alone. They build rings, providers referring to each other, billing agents coordinating across NPIs, patients recruited as props in phantom treatment schemes. The moment you understand fraud as a network behavior, you understand why graph models are not optional. They are the only tool that sees the full crime. But, uh, and this is the thesis of today's episode, not all GNNs see it equally well. So the roadmap that we are going to cover today, we start with the research landscape. As I already mentioned in our previous episodes, we collected a couple of research articles which are synthesized into one coherent picture of where the field stands. Then we go deep into three architectures, GraphSAGE, GAT, and RGCN, not at a survey level, but at the level of what each one actually does to a fraud graph. Then we run the experiment side by side, numbers on a real claims benchmark, and we close with a verdict that is honest about trade-offs, not just a winner's podium. By the time we hit the last slide, you should be able to walk into a room and defend the architecture choice to a CTO or a complaints officer. That's the bar. Now, I know we have touched fraud types before, but I want to come at this from a different angle today. Stop thinking about these categories as types of fraud. Start thinking about them as attack surfaces on the graph. First one is the provider fraud. Billing phantom procedures is an attack on the claim submission edge. Next is the collusion rings, which are coordinated referrals and kickbacks. These are the attack on provider to provider edges. Beneficiary fraud is nothing but recruiting patients, selling credentials. This is an attack on patient notes. Prescription abuse is an attack on drug procedure relationships. Every fraud type maps to a specific part of a graph structure, as we discussed earlier on the types of fraud, which means the right GNN architecture is the one that most faithfully models that part of the graph. That connection, fraud type to graph structure to architecture, It's a thread running through this entire episode. So why traditional method falls short? So across the articles that I reviewed for this episode, one finding is so consistent is it stops being a finding and becomes a law. Rule-based systems achieve high precision and catastrophically low recall on novel fraud patterns. Here's the deeper insight most people skip past. It's not that rule-based systems are badly built. It's that they are solving the wrong version of the problem. They are optimized to catch fraud that looks like past fraud. The moment a ring rotates, billing codes fragment volumes across NPIs or recruits a new set of providers, the rules go dark. Classical ML like XGBoost, Random Forest closes some of that gap, but it introduces a structural blindness that no feature engineering can fix. It treats every claim as an island. It has no concept of who submitted this claim, who referred this patient, or which providers share this patient's history. Isolating claims ignores the most critical signal in the entire data set. The graph context is the fraud signal. The architecture choices we are about to discuss exist because of this exact limitation. Before we touch a single architecture, I want to spend a moment on something that is undervalued in GNN articles, whatever that I have gone through. Graph construction is a design decision and it has more impact on your results than your choice of model. Every claim carries a provider NPI, a patient ID, a diagnosis code. It's nothing but ICD-10. That's the prefix that usually starts, and a procedure code. It starts with CPT and potentially a drug code NDC. Each becomes a node type here. So if you want to add more nodes like attorney that we discussed in the previous episodes, you can add that as a node. So each relationship becomes an edge type with semantically distinct meaning. A provider submitting a claim to a patient is not the same signal as that provider referring the patient to another provider, which is not the same as two providers sharing the identical diagnosis cluster. These are different edges. Collapsing them into one is where you lose the fraud signal before your model even sees it. The pipeline here shows raw claims to entity extraction, to edge extraction, to a heterogeneous claim graph. It sounds mechanical, but every decision in that pipeline is a hypothesis about where fraud hides. Get it wrong, and even the best architecture can't recover. So these are the three contenders, each built on a fundamentally different idea about what matters in a graph. GraphSAGE says, I don't need to see the whole neighborhood. I will sample it and scale. So this is the concept or the theme behind GraphSAGE. On the other hand, GAT says not all neighbors are equal. I will learn which ones I trust. On the other one, RGCN, which is a relational graph convolutional network, says not all edges are equal. I will learn a different transformation for each relationship type. Those three philosophies produce measurably different performance profiles on fraud data. Let's go deep on each one. GraphSAGE, which is the core innovation, is inductive learning through neighborhood sampling. Instead of computing embeddings over the full graph, which doesn't scale past a few million nodes, it samples a fixed size neighborhood and aggregates those features. Here's what genuinely underappreciated about this for fraud detection. Because GraphSAGE is inductive, it can generate embeddings for nodes it has never seen during training. New providers enroll in Medicare every single day. A transductive model, one that only knows nodes from the training graph, is blind to every new provider at inference time. GraphSAGE handles this gracefully, which is a non-negotiable property for any fraud detection system. The LSTM aggregator variant is particularly valuable for claims data. It treats the provider provider's claim sequence as an ordered temporal history. If a provider who has spent 5 years billing routine office visits suddenly pivots to high-cost oncology procedures, GraphSAGE LSTM aggregators captures that trajectory. But here's the failure mode, and I want you to hold this carefully. That is nothing but the low-degree fraud nodes. Sophisticated rings deliberately keep certain providers at 2 or 3 claims per month. Just enough to look legitimate, not enough to trigger audit thresholds. For GraphSAGE, a two-node neighborhood produces a weak, indiscriminate embedding. Those are the front nodes. A well-designed ring deploys specifically because they are hard to detect. GraphSAGE misses them by design. Now we will look into the next one, GAT. So this is the graph attention mechanism. So that's what it is going to talk about. GAT makes one deceptively simple change to graph aggregation. It learns which neighbors to pay attention to. For each edge in the graph, GAT computes an attention coefficient and learns code that reflects how much that neighbor should influence the central node's embedding. With multi-head attention, typically up to 8 heads, the model captures multiple types of relational signals simultaneously and averages across them for stability. Here's why this is so powerful for fraud. In a legitimate provider's neighborhood, the overwhelming majority of connections are benign. In a fraudulent provider's neighborhood, there might be one or two highly suspicious co-billing relationships buried in a sea of 50 legitimate ones. A uniform aggregator lets the majority drown out the minority. GAT's attention mechanism learns to invert that dynamic, upweighting the suspicious neighbors and suppressing the noise. But here's the protection insight that 5 of 10 articles explicitly flag GAT's attention weights are natively auditable. They are computed during the forward pass, zero additional latency. When an investigator asks why this provider was flagged, you hand them a ranked list of specific co-billing relationships that drove the score. Under CMS audit requirements, the traceability can be the difference between a model that passes complaints review and one that doesn't. Now the failure mode that we need to know here is the attention collapse in homogeneous rings. When every provider in a fraud ring has deliberately similar claim profiles, attentions weights equalize. A sophisticated fraudster who understands how GAT works can engineer around it. Now the RGCN, which is a relational graph convolutional network, starts from a different premise entirely. In a heterogeneous graph, the type of edge carries as much information as the node it connects. So if you want to understand what is heterogeneous graph and homogeneous graph, just you can like visit my previous episodes. So RGCN applies a separate weight matrix to each relation type in the graph. A provider to patient treatment edge gets one learned transformation. A provider to provider referral edge gets a completely different one. A patient to diagnosis edge gets another. The model doesn't collapse all of these. It keeps them distinct and learns which relation type are most predictive of fraud. Think about what that means for detection. A kickback ring exploits referral edges. Upcoding fraud shows up in diagnosis to procedure edges. Identity theft lives in patient to provider edges. If you are using a homogeneous GNN, all of those signals get averaged together. RGCN separates them and the results reflect it. So the failure mode here is the compute cost and data sparsity. On a large graph, that expensive training in our benchmark versus our GraphSAGE benchmark, right? For edge types with fewer than 500 training samples, the weight matrices are undertrained. Novel fraud schemes can deliberately exploit RGCN's sparse relations blind spot. Now we will have a head-to-head comparison between different models. Here's what things gets interesting because the comparison table reveals a pattern that individual architecture discussions don't fully expose. Look across the rows there. So we have a different set of criteria to compare across the models. Okay, so one is the scalability, right? So if you see from scalability perspective, the best is this GraphSAGE. From fraud signal perspective, RGCN leads because the relation-specific transformations are the most faithful transfer representation of how fraud operates and the class imbalance. Robustness, the GAT is the strongest among the three. Attention naturally dampens noise from the overwhelming legitimate majority during aggregation. So the key pattern here is no single architecture leads across all six criteria. This is not a flaw in the comparison, it's a signal. The architectures have genuinely different strengths corresponding to genuinely different operational constraints. The question is never which is best in absolute terms. It's always which is best for my graph structure and my production requirements. Temporal modeling deserves a specific callout. GraphSAGE handles it natively via the LSTM aggregator. GAT and RGCN both require explicit augmentation. Temporal edge features or separate temporal graph channels. This is not a minor gap. We are about to see exactly why. Let's make all of this concrete. The 2012 Miami Medicare fraud bust. $200 millions, 90 clinics, hundreds of recruited patients paid to sign blank treatment forms for phantom services. The ring was engineered to evade rule-based detection. Claims were fragmented across multiple NPIs so that no single provider crossed an audit threshold. Each clinic looked clean in isolation. The fraud only becomes visible at the network level. This is the case of why graph modeling is non-negotiable for organized frauds. When you model this ring as a graph, the structure becomes algorithmically obvious. Dense interconnections between provider nodes, hundreds of patients sharing identical codes, ICD-10 codes, all built on the same dates, referring to the same phantom therapy providers. Now watch how each architecture sees it differently. GraphSAGE detected abnormal embedding clusters among co-billing providers. The LSTM aggregator picked up temporal synchrony of claims filed simultaneously across clinics. The GAT attention weights spiked specifically on edges connecting recruited beneficiaries to phantom therapy nodes. The most anomalous connections in the neighborhood. RGCN flagged the dense cross-referral subgraphs through its referral edge matrix and separately flagged ICD-10 clustering through its diagnosis edge matrix. Three architectures, three different angles on the same ring. This is why the cascade matters. Each model sees what the other partially miss. Now the most um, important feature is the spatiotemporal constraints. A class of fraud that purely structural GNNs are completely blind to and it's exploited constantly. A provider billing 50 patients on a single day. A patient receiving chemotherapy at a clinic in Miami and a clinic in Chicago on the same day. These are impossible claims. But a model that only sees graph topology never asks when or where. So it can't see the impossibility. The spatiotemporal constraints, research encodes times as edges, claims within a 30-day window get temporal connections, and location as node features tied to clinic geolocation. With this enrichment alone, all three architectures improve recall to an extent, right? This is not a marginal gain from a modeling tweak. This is structural lift from asking a question the base models ignore. Is this sequence of claims physically or temporally possible? Fraudsters operate in time. Models that ignore time leave double-digit recall on the table every single time. This is RGCN's home turf, and it describes the most sophisticated architectural innovation in this research body. Instead of one monolithic graph, the multi-channel approach builds separate graph channels per entity type. A provider co-billing graph, a patient diagnosis co-occurrence graph, a drug procedure temporal graph. Each channel gets its own RGCN weight matrix. Then a graph level attention mechanism fuses the channel embeddings into a final fraud score. Here's why this matters operationally. The provider channel surfaces collusion rings through co-billing density. The diagnosis channel surfaces upcoding through anomalous ICD-10 co-occurrences. The temporal channel surfaces impossible service sequences, and a monolithic graph averages all of these signals together. The multi-channel keeps them separated until fusion, where the model learns which channel is most informative for this specific node at this moment. That's a far more faithful representation of how healthcare fraud actually operates, and and a direct consequence of that faithfulness. Now, this is the experimental setup, the claim graph benchmark. So we are going to take a Medicare CMS public data set for our implementation. So I'm going to show you the implementation shortly. So for now, I'm skipping this, even this also, because only when we implement, uh, we can see the results in practical. So now with even this discussion is also makes sense when we discuss along with the results. So I'm going to take you through the GNN and few more architecture implementation. So let's um, wind up on here. Uh, we can quickly start our implementation of the pipeline with the real data set, that CMS public data set, right? Shortly. So before winding up, I just want to explain that uh, the decision framework of different architectures that we have discussed here. So genuinely, like the heterogeneous graphs that we were discussing, it has the multiple nodes and edge types. It computes the engineering team in place like RGCN. Most faithful architecture fits to real claims data. So the native explainability required, compliance team needs audit trails. Every flag has to be justified to an investigator or regulator, which is in GAT. And for GraphSAGE, the massive claim volumes daily, fast retraining cycles needed, first GNN system in the organization, quick ROI story required. So meaningful lift over classical baselines at a fraction of the infrastructure cost. So the architectures that we discussed here is not a pure technical choice. It's a function of a graph structure, computation budget, investigator bandwidth, and regulatory environment. So whichever is matching for your requirement, you can go with that. So it's not always required that we need to go with GraphSAGE or RGCN or GAT. It depends on we are, what's our requirement is. So I just want to highlight what from models perspective, um, and from graphs perspective, I want to highlight few points. One is the graph structure, which is non-negotiable. So in every research article that I have gone through, which is introducing a graph-based method, outperformed its non-graph baseline by a minimum of 8 F1 points. The relational signals is too strong to ignore. The second is the temporal context, which boosts everything. So spatial temporal constraints that we discussed earlier. So I improve the recall when we include the temporal information. So models that ignore time leave double-digit recall on the table. that we already discussed. 3. That class imbalance is a defining engineering challenge. So focal loss plus grapha where oversampling is the consensus fix. So get this wrong and your architecture choice becomes irrelevant. Fourth one is the explainability, which is no longer optional. So 5 out of 10 papers explicitly addressed it. Regulatory pressure and operational necessity are converging. Black box models won't survey procurement at a major layer, payer. Finally, the verdict, right? So again, this verdict also, I just want to take you through once after our implementation. I'll explain you in detail. So there are three things to remember from this entire episode. So one is the match architecture, like with your graph heterogeneity. If your claim data has multiple node types and edge types, and it does, RGCN is the most faithful fit, right? So don't flatten a heterogeneous graph into a homogeneous one for convenience. Please note this point because this might be useful for your implementation as well. So you leave measurable performance on the table. Okay, so please make sure, please don't flatten any heterogeneous graph into a homogeneous one for your convenience or for model convenience, because I have noticed that. So GAT attention is an operational superpower. In a regulatory industry, explainability is a system requirement, not a model feature. GAT's native attention weights give investigators an immediate zero latency auditable explanation for every flag. No post ad hoc method fully replicates this. In production, this single property can determine regulatory approval. Third, plan for ensembles from day one. The failure mode analysis is unambiguous. GraphSAGE misses low degree nodes. GAT collapses on homogeneous rings. RGCN struggles with sparse relations. These blind spots are structurally complementary. A cascade that combines all three covers what no signal architecture can. Design for that from the beginning. Don't bolt it on later. So make sure that you remember all these 3 points when you start your implementation. And thank you so much. Quickly, we will see our implementation. Thank you.